Understanding trigonometric ratios. Now this is a very important video where I'm trying to relate special triangles with unit circle. Now at times I've seen why two standards, and when there are two standards we don't have anything to relate them, and that creates a lot of confusion amongst the students. So before moving on with finding trigonometric ratios and all those things, I thought it important to deal with the basics, and the basic here is to understand what special triangles are and what unit circle is and how are they related. So it's a quick reminder on special triangles. So we have two basic special triangles. One is for 45 degrees, which is like this, right? And then in 45 degrees we say, well, if the sides are 1 and 1, then hypotenuse is square root 2, and these angles are 45 degrees. So let me write angles in a different ink. Okay, so this is 45 degrees and that is 90 degrees, correct? So that is one special triangle, which is 45, 45, 90. The other one is equilateral triangle cut into half. So that's the equilateral triangle, and when you have an equilateral triangle, all the angles are 60 degrees, correct? So you have 60 degrees here. Now if I cut it in half, then what happens? Then we also get 30 degrees. So this angle becomes 30 degrees. So we have 60, 30, and of course 90 degrees, the perpendicular. Now what happens to the sides? Let's say equilateral triangle has sides of 2, half will be 1, and this will be 2 square minus 1 square square root, which is 4 minus 1 square root 3. So that is your special angle triangle, and this triangle can be used for both 60 degrees if you look from this side, and for 30 degrees if you look from that side, correct? So basically we have two special triangles, but this one we say this one is 30, 60, 90 degrees triangle, and this one is 45, 45 and 90 degrees. So these two are very special triangles for us. Now in a unit circle, what happens? In unit circle, if you see, what is the radius of a unit circle? So let's draw a line here, for example, and say, well, the radius of the unit circle should be 1, correct? Because the radius is 1, right? Unit means 1, correct? Now if we see our special triangles, that hypotenuse is kind of the radius of your unit circle, correct? And that represents y, and this represents x value. Imagine placing this triangle right here, correct? So you get your triangle, but in unit circle the hypotenuse, which is here, and the radius here, they don't match. In your special triangle 45 degrees and 90 degrees, hypotenuse is square root 2, and in the other it is 2. So it doesn't really match, and that causes a lot of confusion. So what I did was that I created this video for you so that you can appreciate how they are related. And now let's normalize them, means kind of let's make the hypotenuse 1. So we'll redraw these triangles, and these are modified special triangles, correct? So modified in a way that still we do have the same angles and same things. Ratios are exactly the same. There is no change. There can't be, right? If it's 45, these two sides have to be equal, correct? Now to make it 1, what we can do is we can divide by square root 2. So if I divide all the three sides by square root 2, what do I get? Square root 2 divided by 2 is 1, correct? And here 1 divided by square root 2. This is what I get here. And this side becomes also 1 divided by square root 2. So my special triangle now looks like this, correct? It's kind of complicated, but well, you'll find it meaningful when we translate these things on the other side. Now let's look into the other 30 degrees, 60 degrees and 90 degrees. I am purposely making it slightly bigger. Okay, and we will This is an equilateral triangle with 60 degrees, and we will normalize this also. So this is 60 degrees, that one is 30 degrees for us, and this is 90 degrees, correct? Now here, to make this hypotenuse 1, I need to divide by 2. So I divide by 2, and what do I get? 2 divided by 2 is 1, and this side becomes half, and that becomes square root 3 over 2. So that happens with the sides. Now, clearly you will see that the values are complicated, right? They are not kind of whole numbers, but they are kind of fractions with square roots and all. Becomes more complicated. But I think they are very useful. In what way are they useful? Now let's look into our trigonometric ratios, for example, right? Let's say, what is sine of 60 degrees, right? What is sine of 60 degrees? If you see from this triangle, then sine of 60 degrees is square root 3, that is the opposite side, divided by 2, the hypotenuse, right? So you get square root 3 divided by 2. Now how about this triangle? Now you get square root 3 divided by 2 is already the opposite side. Do you see that? And divided by 1. So basically it is the opposite side, right? It is square root 3 over 2. Perfect. So it gives you sine of 60 degrees straight, right? How about cos of 60 degrees? Now cos of 60 degrees is adjacent over hypotenuse. It is half. If you see from here 1 over 2, you get the same value. So there is definitely a huge advantage when we move from this to this triangle. Do you see that? Now basically, opposite side and adjacent sides are your sine and cosine values of their respective angle, right? Opposite side is sine of 60 and adjacent side is cos of 60. Well, does it work for all the triangles? Let's check it out. What is sine of 45? Sine of 45 degrees is 1 over square root 2. Perfect. 1 over square root 2. It matches. How about sine of 30 degrees? For 30 degrees, we need to look here. Now, opposite side of 30 degrees is half, so it is half. Does it work from here? Yes, it does. 1 divided by 2. So that's the beauty of kind of changing the hypotenuse to 1. And that leads to a very important thing. If we can straight away read sine and cosine from the side, that's a good idea to use 1 as in hypotenuse. Perfect. And so unit circle has a huge advantage. The advantage here is that every point here, the x value corresponds to the adjacent side, which becomes cosine, and the y value corresponds to the opposite side, which becomes sine of that angle. So that is the huge advantage which we get from the unit circle. And therefore, in general, any point here which could be written in the form of x comma y is basically what? It is cos of the angle theta. Let's say this is the angle theta. Is basically cos of theta comma sine of theta. And scientists have been using this, mathematicians have been using this for a very, very long time. And they are called polar coordinates. Now, this is when the radius is 1. If the radius is r, they get multiplied by r. That is it. So that is how a polar coordinate or a coordinate on a plane can be specified. So see, x value corresponds to cos and y corresponds to sine. And if the radius is not 1, r, something else, then they get multiplied by r. That's so easy, right? Now, let's fill in the values for our circle. And now what we will do is, we'll fill in the values for 45 degrees first. And let's see how does that work. So imagine this is bisecting 90 degrees. That is 90 degrees, you know that, right? So we will draw this line, and we will draw this line all the quadrants. Let's divide each quadrant into equal half. So when I do so, then I'm basically making 45 degrees, correct? So these are all 45 degrees, and their quadrant should be what? Let's put the values. 45 degrees, we'll use this. Think, I will cut this triangle from here and place it here. when I place it here, 1, that is my 1, right? Unit circle, 1. And that is my y value, and this is my x value. So x value is 1 over, let's say if I drop it here, right? In that case, imagine this triangle there, then this is 1 over square root 2. So the x value here is 1 over square root 2. And the y value is also 1 over square root 2. As you know, for 45 degrees, sine and cosine are equal. And that is your cosine of 45, and this is the sine value of 45 degrees, correct? Now, let's go to quadrant 2. Now, as you move from quadrant 1, this is quadrant 1, to quadrant 2, what happens? Well, the x values become negative, and the y remains positive. Therefore, this will have a value of minus 1 over square root 2 for the x, and 1 over square root 2 for y. Perfect. If you move down to quadrant 3, then what happens? Then both are negative. Perfect. Because you are going negative y, negative x. So we have our value as minus 1 over square root 2 and minus 1 over square root 2. How about quadrant 4? In quadrant 4, x becomes positive, but y remains negative. And therefore, we have a value here positive for x and negative for y. So that's how we can fill our unit circle. This is for 45 degrees, right? And now let's do 30 degrees. Now for 30 degrees, how should it get modified? 30 degrees means 1/3 of 90. So this is 90. I need to divide this into 3 equal parts. So let me do it like this. This is one part, and let's say this is my next part, right? So that gives me 30, 60, 90. Perfect. So this is my 30 degrees, right? So another, I'll just extend this here and get my 30 degrees. That's my 30 degrees, right? And then I will do here 30 degrees, another 30 degrees. Well, I should have used a different ink for 60. Well, but I just hurriedly did it. Anyway, so let's just do 30 degrees now. And that's my 30 degrees, and that's another 30 degrees. So I just split into many 30 degrees, right? Let's go back to 30 degrees triangle. So if you see the 30 degrees triangle, there you are. Opposite to 30 degrees is sine value, and adjacent with 30 degrees is your cosine value. Is that okay? Adjacent value, right? It looks vertical, but you have to see the triangle upside at rotated, right? So that you have to fit in here in this 30 degrees, correct? So if this angle is 30 degrees, adjacent side is always between the angle and 90 degrees. So adjacent side is the cosine, which is square root 3 over 2. Perfect. So cos of 30 degrees is square root 3 over 2. So we get 30 degrees as square root 3 over 2 as the cos value, and for sine it is half. The opposite to sine, it is half. So you get 30 degrees here, which is this much. Now let's look into 30 degrees in quadrant 2. So that angle is 30 degrees for us. Now what is the value here? In quadrant 2, x values become negative. So we have negative square root 3 over 2, but positive half, which is the sine value. And in quadrant 3, both are negative. So we get negative square root 3 over 2 and negative half. And here we have x as positive, which is square root 3 over 2, but sine becomes negative, which is minus half. So that gives us the 30 degrees, correct? Now let's get to the 60 degrees. Now what I will do is I will put a double line for 60 degrees so that there is not much confusion. 60 degrees is dividing this 180 into 3 parts. So that's my first part and that's my second, right? So that gives me 3 parts. And here is the fourth, this quadrant 1, and then this. Well, this is like very close to this one. So anyway, so it is 30, 60, 90, and here we have another one which is kind of, let me just duplicate this one, 60 from here, okay? Now that is what I have my 60 degrees. For 60 degrees, let me write down my values. Now, so let's write in this different thing. 60 degrees, if you see from here, the cos value is half, but the sine is square root 3 over 2. So we get here as half for cos and square root 3 over 2 for sine. X values are positive, y are positive in quadrant 1. Here x becomes negative. So we have negative of half and positive of y value, which is square root 3 over 2, right? And in this quadrant, both are negative. So we have negative half and negative of square root 3 over 2. And in this quadrant, x remains positive. Perfect. And so we have half for x and the y value is square root 3 over 2. It makes sense, right? So, y is negative. Correct? Now you see in quadrant 4, cost rule. You remember that? Cost rule says that cos is positive here, right? C, A, all are positive. Sin S and T, tan, right? Tan is positive. It is ratio of x, y over x, right? When you do two negatives, it becomes positive, right? So, tan is positive. For cos, x value, see, it is positive. All x values are positive, right? Here, y values are positive, rather, sine values are positive. So what I've tried to show you here is a correlation between our special triangles and the unit circle. The beauty of unit circle is that from the x coordinate, you get the cosine value, and for the y coordinate, you get the sine value for 360 degrees. If you are doing the work in radians, now let me get back to that. If you are doing the work in radians, in that case, the angles are very similar, right? Angles are same. The values are same, but the angles instead of degrees get translated to radians, right? For radians, pi by 6 is for 30 degrees, pi by 3 is for 60 degrees, and pi by 2 is for 90 degrees, correct? 45 is pi by 2 divided by 2, that gives us pi by 4. So we have pi by 4s and pi by 2 for our second triangle. So that is how it really changes, but otherwise it is same. So let me write down here to make it very simple that this line was for 30 degrees, this is for 45 degrees, and that is for 60 degrees, correct? So that is our basic line, and this is 0 degrees, and that one is 90 degrees. Now, it's a good idea not to miss 90 and 0. Good, I came here, and for this is a unit circle, correct? So the x value here is 1 and the y is 0, and that's a beautiful value for both sine and cos. Cos is 1 for 0 degrees and sine is 0. Now for 90 degrees, it is, what is x value? X don't move, right? And y is 1, so 0 and 1, correct? And here for 180 degrees, it is x value is minus 1 and y is 0. And at this point, your x value is 0 and y is minus 1. So sine of 270 degrees is minus 1 and sine of 270, cos of 270 degrees is 0. So now my circle is full. You understand how we got all this, right? Now if this is 30, 60, 90, 0, 30, 45, 60 and 90, then you can fill up all these also, correct? So you just fill this up by adding and subtracting, these numbers. So anyway, this is 60, then you can go by 2 times 120, and that is 180. Like this, you can very easily fill in all your 60s, right? And this is 240 degrees. Does it make sense to you? And that becomes 300 degrees. Let me write like this, and this becomes 360 degrees. Perfect. So a very easy way of writing here. And now you can do 45 degrees, right? 45 degrees, 90 degrees, add 45, you get 135 degrees, okay? Now 135 degrees, I can write like this, and then like this. This is 270 degrees for you. And then you add another 45 degrees to come to 180, and 180 plus 45 gives you 225 degrees right there. And 180 plus 30 degrees gives you 210 degrees. So like this, you can fill this up, right? 180 minus 30 degrees is 150 degrees. There you go. And that is your 330 degrees. So these lines are corresponding to the angles which I have just written there, correct? So that completes our unit circle. And the beauty is, actually, they are the same things. But when you're talking about special triangles, we are trying to avoid fractions while writing values here. And that is the reason why we have a 30, 60, 90 triangle with these sides as, 1 square root 3 and 2. And 45 degrees, we are having 1 square root 2. But if we make hypotenuse as 1, then we get the values of 1 over square root 2, 1 over square root 2, and 1, which can be translated to a unit circle and which can directly read the values of cosine and sine of the respective angle. So that is how the things are when we are working with these sines and cosines, correct? So that's where we are, and that is how you should look into. And both are the base for us to find sine, cosine of any angle. And remember, tan is just a ratio of sine over cosine. So once you know sine and cosine, you know tan also. Perfect. So tan in any case is the value of y over x. Let me just write here in a part, like we say, tan of x will be y over x in case we are considering a polar coordinates, right? So tan is sine theta over cos theta is tan theta, correct? So that is how we are. We'll just write here tan theta equals to sine theta over cos theta, and in this quadrant it actually means the value of sine theta is value of y, so we say y over the value of x. So that is what tan theta is. But for sine and cosine, you can straight read the values. I hope you find this meaningful and very important. Refer to this whenever required, and this is going to help you a lot while doing any trigonometric problem. All the best. Thank you.